Okay, so in this very quick video, we're going to have a look at how a fluorescent tube, or sometimes they're known as mercury vapor tube, works. These are the old school lighting tubes that you still find in a lot of old office buildings, and the principles behind it lie with wave-particle duality, the photon nature of light, and excitation and de-excitation of electrons. So this is what our fluorescent tube looks like. And when you switch it on, you have a starter unit that provides enough energy to get the whole thing running. You've got your filament electrodes either end, and that means that you are effectively able to run a current through the mercury vapour and the free electrons that are within that mercury vapour. So if we take a closer look at the actual light itself, you have got a fluorescent coating on the inside of the glass, and that fluorescent coating just means it will give off light if photons of a certain energy interact with it. Inside you have mercury vapour, so a metallic vapour at a very low pressure. It has to be at a low pressure to prevent electrons from interacting and being absorbed by other atoms and molecules inside. And of course, each of those atoms has got electrons orbiting. So when you switch the light on, a current can flow through our gas. Mercury vapour inside can be ionized by interacting with these electrons, and that releases free electrons. Those free electrons are then able to move on and interact with the orbital electrons of other mercury atoms. And when this happens, they're able to excite those mercury atoms to a higher energy state, or rather they're able to give energy to an electron in the ground state to jump up 2 energy levels to the 5.7 eV level. Now there are 2 possible transitions that this electron can make. It can either drop from the 5.7 to the 4.9, or it can drop from 5.7 to 0 eV, or from 4.9 to 0 eV. So there's actually 3, sorry. When it does a lower energy transition, because E is equal to hc over lambda, that wavelength there is going to be relatively long, and it's going to correspond to infrared, which is not visible. For the higher energy level transitions, because E is equal to hc over lambda, a higher energy means a shorter wavelength, but a higher frequency, and that corresponds to a UV photon, which is also not visible. However, that UV photon is then able to be absorbed by an electron in the ground state of the fluorescent coating. So that electron absorbs the UV photon, gets excited up multiple energy levels, and then one of the transitions produces a photon of visible light. And it is that de-excitation and subsequent release of a photon that allows us to see light when we switch our mercury lamp on.